Hello student, welcome to tutorial 1A for single condensable component. Okay, this is today we will do a question related to single condensable component in gas liquid equilibrium in multi-phase systems. Okay, so we have this question. Actually, this is a question in your textbook. I'll just use this question to give you because this is a basic concept of a single condensable component. I think this is a good question. I just want to show you how actually this question is being solved. Okay, it is actually example 6.3-2 in your textbook. Okay, so it says like this. The question sounds like this. A stream of air at 100 degrees C and 5,260 millimeter mercury contains 10% water by volume. It wants us in part A to calculate the dew point and degrees of superheat of the gas. You have seen this dew point, degrees of superheat in the in the second lecture in multi-phase systems. So you can refer back to my video lecture for video lecture multi-phase system number part 2. So you'll find this dew point and degrees of superheat. Okay, so the question wants you to calculate dew point and also degrees of superheat. In order to do this, you have to determine you have to determine in this system. So I draw this one. So you have a stream of gas. So this gas contains dry air and also water vapor, because it says here stream of air, and also you have in this gas you have 10% of water by volume. That means 90% is dry air, 10% is the water vapor. Right. So what will be the single condensable component in this system? The single condensable component in this system of gas is water vapor, because all water vapor that can be water vapor that can be condensable in this system if we lower the temperature, right? So therefore, right, so we have identified water vapor as the single condensable component, right? So the question wants us to calculate dew point and degrees of superheat of the gas. So we have to come up with our strategy. In order to calculate dew point and degrees of superheat of the gas, we have to determine first, is our single condensable a superheated vapor? Then we can do this dew point calculation and degrees of superheat calculation. In order to determine whether our single condensable is in superheated state, so we have to use this equality. So this is from the lecture multi-phase system part 2, where you have this in rule number 3 to determine whether our single condensable is superheated vapor. So we will have to use this equality. So our partial pressure of that single condensable must be less than the vapor pressure of that single condensable at temperature of the system. So we have to do this calculation, and then from here then we can determine the dew point TdP from Antoine equation calculation, and then once we get this, then we can calculate degrees of superheat. So the first thing, we have to determine whether our single condensable is actually in superheated state. So we know our single condensable in this system is water. So mole fraction of water in this system is 0.1. How do we get this mole fraction? Is from this information. When you have a gas system, the composition is given by volume composition. So this volume composition is similar to mole fraction. If you have 10% water by volume in this gas system, that means it is 10% of water in terms of mole. Okay, that means so when we change this 10% by volume, is actually in terms of mole fraction is this Yi equivalent to 0.1. Okay, 0.1 mole per mole. right? And you know the system temperature and pressure is 5260 and temperature is at 100 degrees C. So the first strategy just now, we need to check whether the system is superheated or saturated. So first of all, we have to do this. This is from our second lecture in our part 2 multiphase system lecture, part 2. In order to know whether it's superheated vapor or saturated vapor, we have to check this equation, right? So if it's superheated vapor, that means if it's superheated vapor, then we will superheated vapor, it has to fulfill this condition. Partial pressure of that single condensable must be less than the vapor pressure of that single condensable at 100 degrees C, because the system temperature is at 100 degrees C. So if it's superheated, partial pressure of water must be less than the vapor pressure of water at 100 degrees C. Okay, then we calculate the partial pressure of water in this system, because this system, the single condensable is water, so we know the vapor mole fraction times with the pressure of the system. So we'll get the partial pressure of water in this stream is this stream of gas is 526 millimeter mercury. Partial pressure of water at 100 degrees C, you use, and to find this you use Antoine equation. So this is how we do the calculation from Antoine equation, and then we obtain the partial pressure of water at 100 degrees C is 700 millimeter mercury. So this is when the liquid becomes this is when liquid water at 100 degrees C, liquid water become vapor. First bubble of vapor is at 700 millimeter mercury or 1 atm, right? The standard condition. So you do the calculation, you will get this. So we see now, is our single condensable is in superheated or saturated condition. So we check this. See, our partial pressure is less than our vapor pressure of that water at 100 degrees C. So our water in this condition is actually superheated vapor. So when we have this, then if it is superheated, then we can calculate dew point and degrees of superheat. So we have to do this calculation first in order for us to calculate dew point and degrees of superheat. So what we have to do to get this dew point degree superheat, we have to determine the superheated vapor condition first. Then we can calculate dew point and degrees of superheat. So from this calculation, so we already obtained that our water vapor in this gas system is actually superheated vapor. Now let's calculate dew point or the point where the superheated vapor becomes saturated vapor. Okay, to find dew point, we have to use rule number 4 from our previous lecture session. So to find T dew point, or the point where the superheated gas becomes saturated, T dew point is the point where superheated vapor becomes saturated vapor. So we have to use this equation. Okay, to find saturated condition, this is the equation, because partial pressure must not exceed the vapor pressure of that pure component at temperature of the system, right? So now we have to use this equation to find TDP, because under Antoine equation have temperature, which we can actually find that temperature. So we have to use this equation. So we know just now partial pressure of this water vapor in this system is 526 from our previous calculation, equal to this partial vapor pressure of water at temperature dew point, which we do not know. Our partial pressure, our actual pressure for water vapor here, partial pressure is only 526. So now we need to know what would be the temperature dew point for this vapor pressure to become saturated, superheated vapor become saturated vapor. So we need to find this temperature, right? So we do this calculation. So in order to, we have to rearrange this, we have to do like this. We have to rearrange where we have to log 10 526 millimeter mercury equivalent to log 10 of this partial vapor pressure water, TDP. So we will have this equation, A minus B, A minus bracket B TDP plus C. This is from Anton equation, but we rearrange so that we can get this temperature. So after we log this part, log 10 of this part, we'll get the value 2.721 equivalent to this value. This A constant from table before. This is a B constant, C constant, TDP. You leave it unknown because you need to find this. So you solve this calculation. So you obtain TDP, the T dew point at 19 degrees C. The first liquid drop of this system water vapor will start to develop liquid. This water vapor becomes first liquid at T temperature dew point 90 degrees C. Okay, so if you have this much of water vapor superheated, it will start to become liquid back at this temperature. If you cool the system to 90 degrees C, this water vapor, instead of vapor, it will come water, the first water droplets at 90 degrees C. So this is how you do calculation to find T dew point. So you have to use Anton equation, but you have to do this type of calculation to get T. In multiphase here, in single condensable, if you need to find T, this is the way. You have to use this type of calculation. Okay, now let's proceed to how to find degrees of superheat. So it's easy because we know the initial temperature of the system was 100 degrees C, and now we know it will become first water droplets at 90 degrees C. So let's find degrees of superheat. Degrees of superheat is the difference between system temperature with the T dew point. So we know the system temperature initially was 100 degrees C minus T dew point, then you get degrees of superheat of 10 degrees C. So this is the method how you calculate dew point and degrees of superheat of the gas. Before you get this information, definitely you have to check first whether your single condensable is in superheated state. Once you get it, after you confirm it's superheated state, then you can calculate the dew point and the degrees of superheat of the gas. So in tutorial 1B, after this, I'm going to show you how to solve mass balance using this concept. Thank you.